About six o'clock, and we should get started. Good evening. This is the International Space Science Institute with an extraordinary online seminar. I am Tilman Spohn. I'm the executive director of the Institute, and I am your host tonight. Tonight's talk was actually planned as a dinner speech for ISI's yearly dinner, in particular celebrating our 25th birthday this year. And Dr. Anny Cazenave has agreed to make it a public online seminar when we learned that the dinner had to be canceled because of the COVID-19 crisis, as so many things these days. Anny is our director for Earth Sciences, and she is a highly honored and often cited expert in sea level rise, not the least in response to climate change. She's the lead author of the chapter on sea level changes of the 4th and 5th IPCC report. This year, Anny received the prestigious Wetleisen Prize, often referred to as the Nobel Prize in Geophysics, for her pioneering work in using satellite data to quantify sea level change and related changes in ice sheet masses, land masses, and freshwater bodies. In 2012, she already received the American Geophysical Union's highest ranking honor, the Bowie Medal. Moreover, she's a member of the French Academy of Sciences, a member of the Légion d'honneur, and of the Ordre National du Mérite, in addition to numerous other honors from around the world. Well, Anny, we're very thankful and proud to have you with us. And without further ado, the floor is yours.
Okay, thank you very much, Tilman, and hello to everyone. So as Tilman said, initially this lecture was intended to be given on the occasion of the dinner celebrating the 25th anniversary of ISI. The dinner unfortunately has been cancelled, but I have the pleasure to give the lecture anyway. So I had full choice of the subject, and as Tilman said, my current research is on sea level rise and global warming, so I could have decided to talk to this topic today, but as I am giving many lectures on sea level rise, I have decided to speak of something else today, something new for me. So during last summer, I read this very passionate book, How to Build a Habitable Planet, the story of Earth from the Big Bang to Humankind, written by two famous Earth scientists, Charlie Langmuir, a geochemist, and Wally Brocker, an oceanographer. I decided to orient my lecture on such a topic. Of course, I am not an expert in detail of everything, but I think it's a very interesting topic. So I borrowed the title of my lecture to another very interesting book that was published about a little more than 30 years ago by Ishtiaq Rasool, when he was director of the Global Change Program at NASA. So the title of his book, shown on this figure, is La Terre, une planète pas comme les autres. So in English, the Earth, a planet like no other. So this is the outline of my presentation. I will start with presenting a number of broad features of the Earth, what I call the Earth ID. Gravity, rotation, tectonics, magnetic fields, water content, etc. This will be followed by a list of necessary conditions to build a habitable planet. Of course, the Earth example, because we don't know anything else at this moment. I will talk about the importance of stability of climate over geological timescale. Then also evolution in the recent millennia and centuries. The demography increase and the use of fossil energy, and the grand challenge that our present day world is faced to. And I will finish by the United Nations Agenda 2030 Agenda about sustainable development goals and the role of space, giving a few examples. So let me start with the Earth ID. So, as you know, the Earth's position in the solar system is in the habitability zone, which means that it receives enough energy from the star, from the sun, and it is at a distance where water it can be liquid at the surface. So the Earth rotates in 24 hours about an axis that is close to the axis of inertia of the Earth. In the past, in fact, this rotation was faster. For example, 400 million years ago, it was 21, the length of day was 21 hours, and the rotation slowed down because of tidal friction. As you have seen, the axis of rotation oscillate in space. This is the well-known motion called precession and nutation that are caused by the gravitational attraction of the moon and sun on the equatorial bulge of the Earth. But what is important to mention is that the mean position of this axis of rotation in space remain almost fixed over all the Earth's history. And this is because of the presence of the moon that has stabilized the Earth's axis of rotation, or equivalently what we call the obliquity, that is the angle between the Earth's equator and the ecliptic. And this obliquity excursion did not exceed 1 or 2 degrees. And this has prevented the moon, the presence of the moon has prevented from very large excursion and drastic climate condition. Another feature of the Earth is that the Earth is far from being a perfect sphere, and this is illustrated on these figures that shows the real shape of the Earth. You can see that large-scale highs and lows. The highs are highlighted by the red and yellow color, and the lows by the blue colors. And the cause of this irregular shape is mantle convection inside the Earth. So here you have a cross-section, a simple cross-section of the Earth. So from top to bottom, you have the solid inner core, and above the liquid outer core, and above the core you have the mantle, and then the lithosphere, which is the solid outer shell of the Earth. So inside the mantle, convective motion consists of rising, hot, partially melted mantle rocks, and sinking currents, cold currents that coincide in many places on Earth with the slab sinking inside the Earth. So the lithosphere is made of a small number of pieces that we call tectonic plates. So the tectonic plates move in relation to each other. The motion are very slow, a few centimeters per year. So this is slow in terms of human time, but in terms of geological times, the plate motion can completely change the surface of the Earth. Just to show you an example, about 200 million years ago, all continents were assembled in a single continent called Pangaea. And continental breakup, continental drift, and continental collision occur several times in the Earth's history. These are called the Wilson cycles. And for example, 1 billion years ago, all continents were again aggregated in a single continent, in a supercontinent called Rodinia, that start to break up about 700 billion years ago. Another very important property of the Earth is its strong dipolar magnetic field. So the magnetic field is caused by electric currents that are generated by motion in the fluid liquid core in response to cooling of the core and heat transfer between the core and the mantle, as a core mantle boundary, and also in response to the solidification of the inner core. This slide summarizes the importance of the magnetic field in planetary evolution, or in our case, on the Earth evolution. So it is generally viewed as a shield against solar wind and cosmic rays. So the presence of a magnetic field is supposed to prevent the atmosphere from being stripped away by solar wind, thus avoiding photodissociation of water vapor in the upper atmosphere by UV radiation, and hydrogen escape into space. We have an evidence of the existence of a magnetic field very early in the history of the Earth, at least 3.5 billion years ago, and this is from the evidence is from old magnetized rocks. But the driver of this early magnetic field is still remain unknown. The solid inner core started to form about 1 billion years ago, and it has been suggested that the increase in the intensity of the magnetic field that resulted from the inner core solidification has played a strong role in the Cambrian explosion of life, of multicellular life, that occurred about 500 million years ago. I move now to the atmosphere. As you know, today the atmosphere is composed of 78% of nitrogen, 21% of oxygen, and the remaining 1% is made of two greenhouse gases, carbon dioxide and water vapor, plus a small proportion of other gases. But the primitive atmosphere was totally devoid of oxygen. It was composed essentially of carbon dioxide, CO2, water vapor, and methane. The oxygen started to be released late in the Earth's history, about 2 billion years ago, as a result of the photosynthetic activity of cyanobacteria. And the today, present day oxygen level in the atmosphere was reached about 600 million years ago, but with some fluctuation through time. So now I move to water. Of course, water is also very important on Earth, in particular liquid surface water. 97% of surface water is contained in the ocean, and the remaining 3% are locked as ice in glaciers and in the ice sheets, Greenland and Antarctica, and as well as fresh liquid water in the aquifers, in rivers, and in lakes. I would like to mention that something that is not very well known, it's the fact that there is as much water in the Earth's mantle as on the surface. And this has very strong implication on the vigor of mantle convection. So the origin of water on Earth is still debated. Two candidates: internal volcanic degassing shortly after the Earth's formation, and later asteroid impacts that delivered water on Earth, and probably these two sources were formed water on Earth. So we also have evidence of a primitive ocean very early in the Earth's history, more than 4 billion years ago. So this figure summarizes in a very simplistic way the evolution of life on Earth. So the Earth was formed 4.5 billion years ago. And we have the most ancient trace of biological activity or trace of life date back to at least 3.5 billion years ago, possibly earlier. And this evidence, among others, there are many evidence, but one evidence is the existence of stromatolites that are sedimentary formation created by photosynthetic cyanobacteria. So as you can see on this figure, over most of the Earth's history, the life was composed of single cell organisms, sometimes organized in colonies. But more complex form of life appeared more or less recently, about 600 million years ago. And a major change occurred 500 million years ago with the Cambrian explosion that I mentioned before. So in this, on this slide are listed all necessary conditions that are needed to make a planet habitable, at least in the Earth example. So we need a stable star, stable sun over several billion years. The planet has to be at an appropriate distance to the sun to have enough energy, to have liquid water on the surface. The orbit needs to be not too much eccentric, and in the case of the Earth, it is almost circular. We need, at least in the case of the solar system, a Jupiter-Saturn orbital resonance, which currently exists, avoiding giant planets to migrate towards the inner solar system and to have destroyed the inner planets in the early time of the solar system. We need a gravity large enough to hold on an atmosphere, a strong magnetic field, this has already been mentioned, appropriate atmospheric composition and the presence of greenhouse gases. I will come back to this issue in a moment. An early formation of an ocean. We need also mineral surfaces for life, early life to develop. The presence of a moon to avoid large excursion of the obliquity. I mentioned that before. And a very important necessary condition also is a relatively stable climate over the whole Earth history over 4.5 billion years. And this occurs in the case of the Earth as a result of a subtle equilibrium of the long-term climate carbon cycle. And this allowed appropriate concentration of CO2 inside the atmosphere. So just to comment a little more about the carbon cycle and its equilibrium. So the carbon cycle results from two antagonist factors, at least over the history of the Earth. One is CO2 emission towards the atmosphere by the Earth's volcanism, and CO2 removal from the atmosphere by chemical erosion of silicate rocks and formation of calcium carbonate sediment that ultimately reach the ocean and are buried on the seafloor. So the drivers are mantle convection and plate tectonics, plus a strong water cycle, in particular during continental breakup. And this occurred for the Earth, and this led to a very strong regulation of atmospheric CO2 over the whole Earth history, which led to mean Earth temperature that remain in the range 0 to 100 degrees C over the last 4 billion years. So this figure illustrates the evolution of the mean Earth temperature over the last 500 million years. So you can see, for example, a warm world, high temperature, about 10 degrees higher than today, about 55 million years ago. It has been proposed that this was due to methane degassing at that time. This warm period was followed by a slow decrease, as you can see. I don't know if I can use my the mouse here. That is due to continent rearrangement. In particular, the motion of Antarctica towards the South Pole, where it is located now, motion of India toward north, and the formation of Himalaya and its collision with Eurasia that led to weathering and removal of CO2 from the atmosphere. The next slide is just to zoom over the past 65 million years. So you can still see the slow cooling of the Earth, the Quaternary glaciation, and our current, our current interglacial. I don't think my mouse is working. Okay, here. Our current interglacial period that is called the Holocene. It started 12,000 years ago and marks the end of the last deglaciation. So Homo sapiens, our species, left Africa about 100,000 years ago, maybe less than that, and it dispersed all around the world. But it is worth to mention that during the last 2 million years, there were several other migrations by archaic human species, and even Homo sapiens migration occur in several waves. So the Holocene, that started exactly 11,700 years ago, marked the beginning of sedentarization of Homo sapiens, the development of agriculture, and the development of early civilizations. And this figure shows the evolution of the human population during the last 12,000 years. So on the present is on the right, past is on the left, and you can see that 12,000 years ago, the human population was only around 50 million, so less than the population of France today. At the beginning of the current era, 2,000 years ago, the population is estimated to around 200 million years. So again, less than the population of Europe today. And you can see this well-known exponential increase during the last 2,000 years. So the next slide shows the high correlation that exists between the evolution of the world population through time. Here it is for the last 2,000 years. Present is on the right and the past is on the left, on which is superimposed the concentration of CO2 inside the atmosphere. And you can see there's a very high correlation between the two curves. That, by the way, is a result of the use of fossil energy. So, long time in the Earth history and human history, let's speak about human history. The sources of energy were limited to the use of wind, water, wood combustion, muscular forces from animals and from humans, yes. And this totally changed in the middle of the 18th centuries. This was the beginning of the Industrial Revolution that started in England by the use of coal. On this animation, you can see the CO2 emission as a function of time and space, geography. So after this started in Northern Europe, expanded in Northern America, and now all over the world. Okay, so the use of fossil energy led to technological innovation and scientific progress, which led to big transformation of the world. And the world during, and here you have a list of course of the world during the last century. This is not an exhaustive list, but just to give a few examples. We had increase in life expectancy, reduction of extreme poverty, access to education and healthcare, etc. However, our present day world, our world today is still faced to a long list of remaining grand challenges. And just to give a few, the permanence of wars, terrorism, migration, persistence of poverty, concentration of wealth, rise of populism, etc., global warming, without speaking of pandemics. So in 2015, the United Nations adopted the 2030 Agenda for Sustainable Development, and they define 17 Sustainable Development Goals, SDGs, that are listed here, that should be reached by the end of this decade, by the way. So among others, we have no poverty, zero hunger, so food security, access to water, resource and water quality, reduction of global warming. We have to fight against the loss of biodiversity, etc., etc. Now, in the remaining of this presentation, because we are at ISI, International Space Science Institute, I would like to focus on the role of space to help in reaching these SDGs. So, as you all know, space-based observation provide a global perspective which contribute to improve understanding of the Earth system. So better understanding of the dynamical interactions that exist between the atmosphere, the ocean, land, surfaces, the ice bodies, solid Earth, even solid Earth, and the human society. And obviously, space is also very helpful for societal application. So on this figure, I have highlighted by the black circles where space observation can help in reaching this 17 or part of these 17 sustainable development goals. For example, it is very useful for food security, for water management, for climate fighting against, or at least understanding how the climate is evolving, also for biodiversity. So in the remaining of this presentation, I will focus on just 3 examples on the use or the help of space to better understand these problems. So one example on climate change, one example on water resources, and the last example will be on food security. So let me start with climate change. I will be brief. I will not go obviously into many details. About a little more than a decade ago, GCOS, the Global Climate Observing System, which is a body created by the World Meteorological Organization, the United Nations Environment Program, and other international organizations, defined a number, a little more than 50 environmental variables called essential climate variables that need to be observed on the long term to understand how our climate is functioning and how it is evolving under natural climate variability, but also under human activity, anthropogenic forcing, so human activities. Among these 50 essential climate variables, about 30 are observable from space. And this led ESA, European Space Agency, to set up about a decade ago a big program called the Climate Change Initiative Program, dedicated to provide or to produce by reprocessing of the observation of several many space missions, a long, accurate record of a number of essential climate variables or environmental variables. And you have an example of these variables on this figure. So this program has a 10-year lifetime, and hopefully it will continue in the future. So it is currently feeding a big program of the European Union called the Copernicus program that is dedicated to the monitoring of the Earth and its environment, using not only space observation, but also in situ observation and modeling in support of climate change and climate change mitigation and adaptation. So this is a very big enterprise that is functioning well, I must say. So my second example is about water resources. Surface waters are continually exchanged between the ocean, the atmosphere, and land surfaces. And on land, water are stored in several reservoirs, for example, in lakes, in rivers, also in groundwater aquifers. But these land water stores vary with time, sometimes space, but mostly time, because of natural climate variability and also because of human activities. And for the management of water resources, for example, for agriculture, for irrigating crops, also for domestic use or for the industry, it is very important for the nations at regional scale to know how much water are stored in these different reservoirs. The problem is that, except in our region in Northern Europe or in North America, in many other regions of the world, the in situ network, for example, in situ gauge networks, are declining, and in some region of the planet, they are even non-existent at all. I will give an example in a moment. So an option, and the very good option that is now used routinely, is to use space observation to monitor water storage on land. So we have different techniques, different kinds of satellites to monitor surface waters, river levels, water level on lakes and storage. It is possible also to monitor soil moisture in the upper layer of the soil, so the water that is used for the vegetation to grow, and also the waters that are stored in aquifers, so called groundwaters. So this is now routinely used to monitor land water storage. Just to show this example of river basin that are devoid of in situ network. This is the example of the Congo Basin in Africa. You can see the blue, light blue line represents the hydrographic network, and the white dots that you can see here are the virtual stations that can be that cover this river basin, the Congo Basin, by satellites. So what is a virtual station? It is explained on the left-hand side, bottom part of this figure. It's simply the intersection of a river, shown in blue here, with the satellite track. What is a satellite track? It's just the projection of the satellite orbit on the surface of the Earth. So each time the satellite crosses a river, it measures, for example, the water level of the river. And through time, we are able to construct long records of water level and deduce, for example, water discharge, which is the quantity of interest in hydrology. So you can see an application of space observation to monitor water resources. So my last example now is on food security. So this figure compares the malnutrition on Earth 30 years ago, at the beginning of the 90s, and what happened about 5 years ago, around 2015. So on the left, you can see the number of people in food insecurity or malnutrition, in a state of malnutrition. They amounted about 1 billion. And this problem affected most Asian region and also the Sahel region in Africa, or sub-Saharan region. You can see on the left-hand side of this figure that the situation improved through time, but we are still faced today with about 800 million of people in suffering hunger. So the situation improved in Eastern Asia and in Southeast Asia, but it became worse in the sub-Saharan Africa and in Southern Asia. And I think in that case, Southern Asia include India. So how space can help to solve this problem. So space observation, in particular satellite imagery in different wave bands, are routinely used now to measure soil condition and vegetation condition on ground, in particular crop growth, water stress in crops, or also crop disease, crop yield. And this was the objective of a big international program called GeoGLAM, that what was developed a few years ago, some years ago, and involved most of the G20 nations, in addition to a number of nations of countries in food insecurity, as well as a number of NGOs and other international organizations. So GeoGLAM is able to provide in near real time at regional, national, and global scale the state of crops. And here you have an example. In Africa, at the date of 28 August 2019, so 1 year ago. So you can see that, for example, the green color corresponds to crops in good condition, but the orange color here corresponds to crops which have problems. I don't know exactly which problem, but either water stress or disease, etc. So solutions have been found by the agricultors to solve the problem. So I am now coming at the end of this presentation. So before closing, I would like to mention that very recently I moved to a new office in my lab in Toulouse, and during this moving, I came across two issues of the Spatial magazine. I had them in my office for many years, but I did not remember. So one issue written by former executive director of EC, Roger Bonnet, who wrote an article on spaceship Earth in 2011. And another issue or article written by our current executive director, Tilman Spohn, written on Planet and Life in 20 and published in 2012. Sorry. So I must say that I did not inspire myself of this article because I found them very recently. But I just note that we are EC are very much interested in this very important problem of habitability and life evolution on Earth. So my last slide, and I will stop there, is first of all to thank you for your attention and remind you that we have no planet B. So thanks to everybody.
Thank you very much, Anny, for this very nice and interesting talk. Yeah, I mean, it is true. There is no planet B. And this is something we all have to be aware of and take care of. Now, Anny has agreed that she would be willing to answer questions. And what we usually do in this seminar series is we have two channels of providing questions. You can either write in the chat channel, in which case I will read the question to Anny and she will then answer it, or you raise your hand and then Saliba, our computer guru, will give the mic to you and you can ask the question in person. So
but I have asked Tilman to help me in answering the question because I am not an expert of all these topics.
Oh, well, you do first. So the first question is, how does the Earth's magnetic field prevent photodissociation of water vapor? Well, that's a good question. I'm not sure I could answer that, but maybe you
can. So go ahead.
No. I mean,
no. Please go ahead.
No, I would not be wanting to answer that as a chemist's question, and no, I'm pointing no. So shall we move on to the next one? What would happen to the Earth if we had no moon? That was the next question.
There have been some studies, in particular by a French colleague, Jacques Lascar, who showed that the gravitational attraction of the moon on Earth, on the Earth's equatorial belt, has prevented, he made a numerical integration in the distant past, and he showed that because the presence of the moon prevented the obliquity to go back to have very large excursion. He showed, for example, that without the moon, the Earth's obliquity could have varied between 0 and 85 degrees. So this would have given rise to very drastic climate change over the whole Earth history, preventing from climate stabilization, as we have seen as an important constraint for life to develop.
Yeah, life needs a stable climate, or it appreciates a stable climate. There is a raised hand. Roger Bonnet has raised his hand. Are you on, Roger?
Yes, I'm on. Can you hear me?
Yes.
Sure.
Yes. Bravo, Anny. C'était formidable. Thank you. Thank you, Anny. You have been fantastic. It's a beautiful talk, and I wish we can discuss that again in the future. I have just one question, which is for me always a concern. You showed how important was the ability to observe the Earth from space. And there is a need to have space observations permanently there. So some country may decide not to provide the instruments that they are providing today, and therefore we may miss something from the system. So I have just a question of curiosity. Who is responsible today to make sure that the space system can be made resilient and can be there with all its components without any too many, let's say, too many problems?
As a past director of ESA, you know the answer better than me, but I can try to answer. It's a big collaboration between the science community and the space agencies, and also the international organisms that provide money, of course. But I can see, for example, in the case of, just to give a particular example, the Climate Change Initiative Program, ESA is asking the science community to provide input to define the future program, and then to continue to process the data, to provide new essential climate variables, and also new quantities like the global water, the global cycle. I did not mention that, but now what we want to have is the information on the global water, energy, and carbon cycle. So this means we have to use in synergy different kinds of variables and different kinds of observations. So it's a collaborative enterprise with different contributions from the science community, the space agencies, and of course the bodies that provide money. So, but you are in a better position than me to comment on that.
Thank you very much. I'm not in a position at all. So, but what I get from your response to my question is that you are very optimistic. And that you don't see any big country getting in trouble and not satisfying all the needs that we expect from it.
Of course, we always want more than we have. But yes, I am rather optimistic, at least for the Earth observation, and in my domain concerning climate change. There are a lot of missions already in orbit functioning, that are currently functioning, that we can use. And there are plans for new missions. If you look at the Sentinel program of ESA and other missions developed by other space agencies, at least for the coming decade, we can be optimistic, I think. Later on, I don't know, but what may happen on Earth, I don't know.
There are questions piling up in the chat channel, so maybe go to the chat channel again. So Klein is asking, do you see a risk of monitoring of the Earth from space due to planned and partially realized mega constellations of satellites? So
I did not understand. I did not understand the question. What is the question?
I think the question is, do you see any danger to Earth observation from those many satellites that are in Earth orbit? And,
I am not an expert of that, but I know that there are people watching this problem, and of course we are not. How do you say that? It can always occur a collision. Is that the question about collision between satellites?
Well, I think it's more general. Whatever, maybe collisions, other risks that might come from that. But
the risk is to have an instrument that is no more functioning, and this happens sometime, and this is a big risk.
Yeah.
But I think the collision risk is another risk, but the probability is
it's
much
risk.
lower than
it's a risk, and
instrumental.
I mean, the agencies are quite concerned about this, actually.
Yes, I am sure. It's not my expertise, but I am sure.
Yeah, then another question from a 97498. One of your slides summarized in the conditions for habitability on Earth and in general. Would you comment on or compare, contrast how these conditions relate to Venus, particularly since Venus is considered Earth's twin?
Okay, I am not an expert of Venus. I have read that for example, one condition that was listed on my slide is the presence of a magnetic field as a shield for the planet. But the case of Venus, Venus has no magnetic field, but a very dense atmosphere. So this is an open question. Of course, I'm not an expert. I have not the answer, but this is really an open question. So it's maybe you, Tillman, you are a planetary scientist. You have the answer.
Well, you know, I mean, this clearly has gone through the greenhouse warming that we may fear for the Earth, but of course much more strongly so, and that has, of course, in part due to the closer orbit of Venus to the Sun. So that is a very important effect in that. So we do not have to fear that we will have the same fate as Venus. But there's a lot of discussion in the community about water being stable on the early Venus, and just how the greenhouse warming came about, and so forth and so forth. And it's an active area of research, and we can learn from Venus, for our own planet. So the question here by host one on ROB is Brussels. The planet B does not exist indeed, but we are good humans. The problem is that we could go into an extinction of the magnetic field, and the atmosphere is evolving in a way that is very scaring. I think that new space with precise agriculture can help. What do you think?
I am not sure I catch all the whole question.
Yeah. I think there's one element in the question that refers to the magnetic field, and that maybe the magnetic field could disappear. But the other
it is currently declining in intensity, but this occurs several times in the Earth's history. There have been many reversals. So from one pole to another, so a period of time with lower intensity. I am not an expert, and I must say that I'm not an expert of most of the questions I have presented in this lecture. I am sorry, except maybe at the very end. But my understanding is that the magnetic field never disappears completely, even during a reversal. So it's what I have read in the literature.
There are three raised hands now, and maybe we can go to the first. Gilles Somaria.
Oh, Gilles.
Gilles, the floor is yours. Can you ask a question?
Could you unmute your microphone, please? Unmute your microphone, please.
Here, do you hear me?
Yes. Bonjour, Gilles.
Bonjour, bonjour. Okay, very impressive talk indeed. Okay, a lot of stuff you have covered, and it's very interesting to have.
I hope I did not say too many wrong things, but.
Well, no, very interesting. Okay, now I was curious about the Jupiter-Saturn orbital resonance. For example, are there simulations that, for example, if you had a solar system without Saturn, what would happen? How long it would take for Jupiter to to change orbit or this kind of thing. Are you aware of that?
I think it is. This refers to the work of, for example, Alessandro Morbidelli.
Yes.
I am sure you are aware of his work, who showed that migration of, but during the early phase of planet formation, there is in general migration of the outer, big outer planets towards the inner, I would not say solar system, but star system. And this is, by the way, I'm not, again, I am sorry, but I am not an expert of that. But the exoplanet observation shows many Jupiter type or Saturn type exoplanet very close to their star. And this is interpreted as a migration towards the inner star system. And if this had occurred on Earth, the Earth, Venus, Mercury, and Mars would not exist. And this did not occur because Saturn prevented Jupiter to migrate towards the Sun. And this is another curious condition or necessary condition to have the permitted the Earth to stay and evolve and life to develop.
Yeah. They call it the
Grant
Grant
It would be interesting to look at that a little more. Yeah.
So, sorry? What did you say, Tilman?
They call it the Grant tack model from sailing, you know. So so Jupiter and Saturn moved inward, and they, you know, according to theory, they would have continued to move, you know, and cleared the inner region where the terrestrial planets were about to form. They weren't formed at the time. But then the resonance between the two caused you know, them to reverse the motion and go outward. But before, they had already compressed the inner region and increased the surface density in there, and allowed then the terrestrial planets to grow. It's a model, but it's a model that it explains why, you know, the inner solar system is devoid of giant planets and instead has nice little small planets, including our Earth. Now there's another. Can we turn to host ROB, host 1 ROB being the Royal Observatory in Belgium, I suppose. You want to?
Yes.
Véronique.
Oh, Veronique. Hi.
Hi. And also putting the questions on the evolution of an extinction of the magnetic field. And the questions also contains one part which is related to precise agriculture. That is the measurements of moisture of the soil in the world. And that, I think, could help in generating more food and trying to overcome what our atmosphere will generate. What do you think about that?
Oh, yes, I did not mention precise agriculture because I could not mention everything, but it is routinely developed now. There are many programs, and a number of farmers are using space to space data, including GPS, but not only Earth images, interpreted Earth images in the optical domain or radar to look at the condition of the crops. So yes, it is, but it is operation. Most in many regions, it is something operational and routinely used, and it is a very important application of space, of course.
We have so many questions. You have to speed up.
So maybe I can. What I propose is I will look at the question, and if I am able to answer, I will do that offline by email. If I am not able, I will ask some support, some help from experts. And
I can
because I
quickly
think,
answer one question. There's a question: will this be recorded and put online? And yes, it will be recorded and put online, just like the others of our seminars. Maybe take another two raised hands if you allow. So Jose Torrejon would be the next, and then Al Hoffman. Is that you, Al Hoffman? So Jose first.
Hello, thank you very much for this nice talk. I have a question, is that those days we have, say, an increasing number of global warming deniers. And these deniers even say that there is no agreement among the scientific community. But of course, it's not the general scientific community which matters, but the climate scientist. So I want to ask you as an expert, what is the level of agreement among climate scientists about the global warming, the existence of the global warming, and B, the fact that this global warming is caused by human activity?
Well, I think that there is a very large agreement among the climate scientist community all around the world about, first, there is global warming, and human activities are the main cause of this global warming. So about climate skeptic, what I would say, I mean, first of all, they are less and less numerous, at least in Europe, maybe not in North America, I don't know, but at least in Europe. And my position is just let them see the facts, the observations. So earlier today, I had a video meeting with the World Climate Organization. That is, we are currently preparing the next state of the global climate report, and we are looking at all climate variables: the temperature, land ice melt, sea level rise, ocean acidification, sea ice decrease, etc., etc. And all these variables, climate variables, go in the same direction. So they either increase or decrease, but the global warming is there, and we see it very well in all observation we can collect from space, from in situ, and so on. And to be sure that it is due to human activities, it's the purpose of the climate modeling that is now well developed by part of the climate community. And this model shows that without anthropogenic forcing, so the greenhouse gases emission, we are unable to explain the trends of all these variables I mentioned before.
All right,
so
I see.
So,
I see. Thank you very much.
Albrecht Hoffmann, could you mute your microphone? Yeah, please speak up.
Can you hear me?
Yes,
Okay.
we can.
My question is about the relationship to polar ice loss and the rise of sea level, which is an obvious one. But my question is a little more specific. You measure from satellites, I think, extremely well the ice loss from the polar regions, Antarctica and the Arctic region. And you've been observing this for, what, 20 years or so? And so you know exactly how much water has been put into the oceans from that.
yes.
Now, if one looks at the actual rise in sea level, that consists of two parts. It's the
Yes.
additional water and also the temperature increase, of course. But can you actually match these independent measures of, or are there independent measures of sea level rise matched to the ice loss
yes.
from the Arctic and Antarctica?
Okay, so we do, it's an exercise that we call the sea level budget closure. So we try to compare how much sea level is rising using altimeter satellites. And on the other hand, using other observing system, we either from space or in situ, we estimate how much the ocean is warming, and this leads to thermal expansion. And we quantify this not using space data, but using in situ data of the Argo program, Argo floats program. And for land ice, Greenland and Antarctica and glaciers, we use other observing system. For example, for the ice sheet Greenland and Antarctica, we use space gravimetry observation from the GRACE mission. It's an American German mission, and we can. It seems that you are an expert. We estimate the mass balance of the ice sheet, and summing up all these individual contribution, ocean warming, ice mass loss from Greenland, Antarctica glaciers, and there is also a small component from terrestrial waters. We can compare with what we observe in terms of global mean sea level evolution. Alors, I must say that if we do this exercise over the altimetry era starting in 1992 to 2017, it works very well. We are in a position to close the sea level budget. So this means that there is no big problem, instrumental problems with one or several observing systems. And this means also that we understand well the processes. But since 2017, we observe that we are no more closing the sea level budget, and we don't know why yet. It's a new open question, and we are working on that. It's probably due to instrumental problem of one of these observing system, but it's ongoing research.
Is there some possibility that this is simply a short-term effect?
No. But I can talk to you more about that offline if you are interested.
Okay. Thank you.
Okay.
Thank you, Ellen. Hi. Well, a few more questions, maybe, if you may, before we close it. One relates to the reduction of air travel due to Corona. Does that have any measurable effect on the evolution of CO2 and the climate?
Oh, certainly, I don't know the number. Maybe you know, I don't know the number. The CO2 emission due to air traffic counts by about, if I remember, 2% of the total CO2 emission, something like that.
3, I thought.
3? Okay, 3. Okay, 3. So reduction of air traffic since the beginning of the pandemic certainly decreased the CO2 emission by, let's say, 2%, something like that.
Oh, it's a small effect.
It's a small effect, yeah, exactly, it's a small effect.
There's a question about the risk of climate cooling in Northern Europe, as a consequence of changes in ocean current paths and intensity.
Okay, so yes, we are very much interested. I mean, the climate science community is very much interested in looking at what we call tipping points, or abrupt change, an irreversible change in the climate system, that could occur during the continuation of global warming. And the shutdown of what we call the thermal incirculation or intensity of Gulf Stream in the North Atlantic is one of the possibility. So far, we don't observe a very robust signal of decrease of the Gulf Stream intensity. But the climate models that are developed to simulate future climate change predicts that if we continue to emit greenhouse gases at the same rate as today, by the end of this century, the thermal incirculation will not stop completely, but could be reduced by a factor of 50% around. And probably this will not have a strong effect on the European climate because this will be compensated by the continuing global warming.
Michel Blanc has a question similar to a question that I had, and he refers to the strong correlation between CO2 in the atmosphere and the growth of the world population. Now, he asked about the relation between the two. For instance, I mean, I would think that the growth is mostly in areas where the CO2 production per capita is low. And in areas where the CO2 production per capita is high, population growth is relatively low. So I was wondering, and he was saying that, I mean, would it actually, if we became CO2 neutral in developed countries, would that help any? If it's so strongly related to population growth?
Well, I don't have the answer. We have to look at the numbers. So I don't know what is. I don't know.
Okay.
You may comment on that, but I don't know. Maybe Michel has a comment on that, an answer.
Well, it's in the chat, so.
Okay. So.
Is there evidence for glacial cycles before the Quaternion, given that the Milankovitch cycles would continue regardless? What conditions initiated the glacial cycles starting about 2 million years ago?
Oh, so I missed the first part of the question, but okay. The second part. You have seen this curve of continuous cooling since 50 million years ago, due to several factors, by the way, not a single factor. So the motion of Antarctica to the South Pole, motion of India, collision of Himalaya with Eurasia, etc. But about 2 million years ago started what we call the Quaternary glaciation. So my understanding is that the exact cause of this is not is still debated. Some people have proposed that it was due to change in the ocean currents or ocean circulation that redistribute heat across the world, and due to the closure of the Panama Isthmus. But the question is still debated because I have read that recent re-estimation of the closure of the Panama Isthmus is most older than 3 million years, 2 or 3 million years, but more probably around 10 million years. So the question is debated, and it's probably the interplay of different factors. So, but maybe I have not the answer, because I'm not an expert again.
Okay, well, it's 1/4 the hour. I think we should come to a close. There are a few questions left, but We'll forward you, or you can look at the questions in the chat channel.
If people want to send me emails directly, my email is I think known. It's anny.cazenave@ecbern.ch. Sorry. Oh.
So I was
I have several other addresses, but anyway. So I will be pleased to respond if I am able.
Yeah. Again, Anny, thank you very, very much. It would have been nice now to go to the dinner after your dinner speech. So we started at the apéro time at 6 o'clock, and now we would have been at the dinner. Unfortunately, we can't because of Corona. But thank you very much again. It was a very nice.
Maybe next time, next year.
Yeah, maybe next year. And to the attendance, thank you very much. We had about 240, 250 or so people joining us, listening in. And I wish everybody a nice evening and a nice weekend, and see you all again some other time. So bye-bye, have a good day.
And bye-bye to all of you, and thanks for attending. Bye-bye.